Welcome, everyone. We're ready to start. Welcome to this course on TCP-IP. My name is Jean-Yves Le Boudec, and I'll be your lecturer for this term. This is a practical course. There's a lot of labs, so we have a large group of TAs that I will introduce now. Our head TA, the one who's responsible for all organizations of the labs, is Roman Rudnik. And he will be assisted by Ehsan. Ehsan is the cameraman in the back. These lectures are taped. You will find on Moodle all the links to view the lectures if you missed one or if you want to see it again. Ehsan. And we have Arpan. Elena, who is not here today because she's writing a proposal. Jagdish was not here today because he's busy with his startup. Tong and Marguerite. So those are the people who will help you in the lab. So you will see them tomorrow in the class to assist with the first lab. So this course is about computer networking. There is no specific requirement other than the general requirements for EPFL master level courses. It's a course that will have a lot to do with practical. So you will have to be familiar with the computer and not afraid of using the computer, and be ready to spend a lot of time in the labs debugging things. That's the practice of computer networking. Computer networking is, like many things in software, and it's primarily software in this course, and like many things in software, is simple, made of simple things, but there are zillions of simple things. So the complexity comes not from a few big complicated things like Fourier transform, that's complicated, how do you know what it is? We don't have things like this, but there are lots of small things. One dilemma when teaching such a course is how to teach all those complicated little things. Fortunately, it's possible. The wrong course would be a 16-credit course where I would teach you all the details of all the protocols of computer networking. But this would not be good. This encyclopedic version would not be very interesting. Chances are you would forget most of it anyhow. The approach we will use, that many teachers use for such courses, is what we call the rake approach. So we have to do a balance between breadth and depth. If we give a course where we cover all topics of TCP/IP, we will be very shallow. If we cover a few topics, we will be very deep. Now, we have only limited time budget and credit budget, so what do we do? And the idea is to go deep into a number of selected topics. Those are the ones that you will do in the labs. And the hope, and you have to trust me and the experience of other people like me, is that by choosing specifically those labs, anything else that you have not done will be in the convex set of what we have done. So it will be easy for you to imagine what it would be based on the experience you will have gained on going deeply into a few things. If you don't go deeply into a few selected topics, you are likely to miss what TCP/IP networking really is about. But we need also a breadth. We need to be aware of the global picture. Another way to tackle this complexity is to separate two questions, what and how. What means, what is this thing doing? And very often associated with what is this thing doing is, why was it invented? Which problem is it solving? This is usually very simple and very fast. Then, how does it do it? For example, we will see that TCP is a protocol for providing reliability. So the problem, one of the problems that TCP solves is packets can be lost, and we need somehow to recover the lost packets. Understanding that is easy. And then you can easily imagine how you would recover lost packets. And probably your imagination will be very close to what TCP really does. Now, the how is typically very complicated, and this is what we will do in the labs. But very often, there is no rocket science behind what is done. Most of the how is the thing you would imagine. So there's no much point remembering it. So one way of compressing information in a very efficient and intelligent way is to know the what, trust your imagination for the how, compare it with what really happens, how it is really done, and then learn the difference. If there's a wow, if there's, oh, they do it in this way, then you've learned something. That's not something you have imagined. If it is, oh yeah, that's how I would have done it, then there's nothing to remember. So that's one way of managing this complexity. Very often, we will use, you will probably use Wikipedia. Wikipedia is a good resource for networking because it's typically done by people who are like me or others who are active in networking. But one of the side effects of Wikipedia is that it tries to cover everything and agree with all different opinions. So it tends to be very verbose and explain the how in very much detail. Not all, but many entries do that. So when you will go to Wikipedia to learn about things, try to separate inside Wikipedia the what from the how. Normally it's done at the beginning of a Wikipedia entry, the what, and the how at the end, but sometimes it's not fully separated. Right? This is similar to using a graphical user interface, a Macintosh, versus the command line in the Macintosh or Unix machines. Doing things, once you know that you have to do something, you find with the menu how to do it, and you don't need to remember how to do it. But if you use the command line, you may need to remember lots of things. In this course, in the labs, unfortunately, very often we will have to use the command line, so the how will be complicated. This is how the course is organized. We are in the lecture room today. Every Thursday, we'll do a lecture. Every Friday is a lab session and a quiz every other Friday. So the lab session is done on your own machine with the exception of one lab. What happens on Friday is that in the room you have TAs who are helping you with your questions, but you can do the lab anywhere, anytime. Just be on time for returning the lab assignment, but you can do it anywhere, anytime. In the past years, we had a request for an extra lab session that was particularly useful for Tong. Yes, thank you, Tong. There's a bug here. It's until 1 o'clock. So Tsong is worried about having to TA until 2 o'clock. No, that's a bug. I will correct that in the final version. It's until 2 o'clock. There's an overflow session that was asked in the past year on Tuesday. That's useful particularly at the beginning for those of you who perhaps don't come from computer science and might take more time. Then we will do this overflow session at least as long as there is a request for it. The quiz is every other Friday, so not tomorrow, but next week there will be one. It's mandatory. It's part of the final grade, as I will explain in a minute. If there are questions, feel free to interrupt now or at any time. We will use primarily the copy of the slides that I'm showing here as the lecture note. If you need more information, I use as a reference one textbook, which is freely available. That's by Olivier Bonaventure in Belgium. For some other parts, there will be some specific notes, but we'll come to that later. A few words about the labs. I give the microphone to Roman.
Okay, so I will give a brief introduction in the organization of the labs and the environment that you will have during lab sessions. So you will have 7 labs in total, so which are mandatory and graded. So as the professor said, the main slot will be on Fridays from 11:15 to 1. Additionally, we have a slot for you on Tuesdays from 4 to 6 in INF 019, which is the Internet workshop room. We allow you to collaborate with groups of 2 people, so you can find a teammate to do the labs together. And also, so all labs will be uploaded on Moodle. and please fill it as the PDF inside. So don't write any other documents. It's not needed. You will have 2 weeks per lab, except lab 0. So usually you upload the labs on Wednesday in the evening, and you also should upload the lab before the next lecture on Wednesday. So in order to emulate a network, we use a mininet, which has a Python-based API. So the virtual machine with the mininet is already on Moodle. You can download it and start playing with it. Also, some labs will require IPv6 IP addresses, which EPFL doesn't provide, but we have it in INF 019. So there is an access point LCA2 TCP-IP labs Wi-Fi that gives you IPv6. So, for example, lab 0 will need the IPv6. The password for this access point will be given to you in the description of the lab 0. So you will need access to INF 019 because, for example, lab 2 is hardware lab, so you have to play a bit with the real hardware. For that, please go to the Moodle and fill the lab rules agreement. I saw that some of you already did. Good job. Please do it before the next Thursday, so then you will have access to INF 019 using your CamiPro. So please keep material in lab in a good state because we have equipment there for you, and keep it clean. So respect the EPFL rules. So a couple of words about first 2 labs, which are very important. So lab 0 is introductory lab. So there you will have some basics about IPv6 and IPv4. And this lab is different from other labs because here you will have only 1 week. So you should upload it next Wednesday before night. So pay attention to it. Also, lab 1 is introduction and the background for the mininet. And so there you will have all details that you will use in the future labs. So please be very careful with this lab, otherwise you will not be able to do other labs. So we know that some of the students have no background in TCP-IP, so that's why you maybe will have to spend more time, and that's why we have to use the time slot. Also, each lab except lab 6 will have an optional research exercise for you that you can do if you want to have extra bonus points for the lab. So TA team here is to help you, so you can ask the questions, but please be as much as dependent as you can. So try to use Google and Stack Overflow because plenty of problems that you will face are already explained there very well. For the report, in each question, please don't write a full summary about what you do. 2 sentences is more than enough. And please don't cheat. It's very easy to recognize, and you will be penalized for that. So in order to communicate with us, so usually all important information is on Moodle. However, now this year we will use the Slack channels for the discussion of the labs and lectures, content of the lectures. So we have 1 Slack channel per lab and 1 channel for the general questions about the course. So we already created the workspace on Slack. So all of you should receive an email till tomorrow. So please, if some of you will not receive this email, let me know. So then you'll be able to register in the Slack. All information about the Slack is also on Moodle. So some of you who haven't used it, please take a look about the rules, how we're going to communicate. You can ask questions there, but please, first, when you ask a question, check if someone of you already not asked it. Let's not create a mess in Slack. You can also answer the questions of other students because we know that some of you are already very familiar with the material. And for that, you will be able to get the bonus. So if you find the answer of other students useful, you can put thumb up. And 2 students with the most big number of thumb ups will give some bonus at the end. So it's 0 to 25 points. So in this way, we want to have a more communication between the students. So enjoy. That's all from my side. Yes.
So I have a question. You have mentioned a few software tools like
Yes.
Net. Will I have any problems if I'm using Linux or Windows or Mac OS?
Well,
Specific or not?
oh, no, you usually not, but we have a virtual machine for you with TCP, with this mininet already installed. It's on Moodle.
Okay.
It will be explained in Lab 1 how to set up it, so shouldn't be any problems with it. Other questions? Okay.
I mentioned that there will be tests. The idea of the tests is to make sure you work continuously and before the labs also, so that because there's a logic between the course and the labs, so you should study the lecture before starting the labs. And to help you make sure you do, then we do tests every other week. Only the 5 best out of 7 are used for grading, so you have two jokers, which means also if you have a dentist appointment or you have to go to hospital or see your mother-in-law at one of the Fridays, then there's no excuse, you will simply skip up to 2. During the tests, like at the exam, there is no document allowed, right? Just a pencil, and then you'll have to tick boxes. No documents allowed. Of course, we will not ask questions that are specific about what is in the 24th bit of this address or things like this. The idea of having no document is to force you to learn the things that I think you should learn. You can look at the tests of the past 2 years. They're online. You can train yourself with the tests using Google Forms, so you can try them and you will have an idea of what is awaiting you. I will also sometimes use SpeakUp, like now. SpeakUp is a tool to poll you, so where I ask question, I would like to have your opinion. Many of you have used it. If you have not used it, you can go to the website that is given there. There's an app that you can download, or you can also open a web browser and go to the address that they give. And as a test, I'm interested in knowing what is the background of all of you. So this poll should be open, and I invite you now to test your SpeakUp and to give me also this information. That's also an opportunity for me to test my handling of SpeakUp. The way I use SpeakUp, you see the answer you are typing in, and when I close the poll, you will see the histogram of all the answers given by the class. Do you see something is? Yes? I don't see many answers. But in the interest of time, I move on. So I close the poll in a few seconds. You have last opportunity to answer. And you will see that I was not very successful in your SpeakUp. So at the break, perhaps you should install SpeakUp so that we can use it in class. Right? SpeakUp allows you to send messages in class anonymously, but I have to warn you, you have to do it ethically. You cannot use it to abuse other people or do things that are illegal to do anywhere, right? If that happens, we can make SpeakUp non-anonymous. Right? The exam is also, which is in the exam session, is also closed book. No document is allowed. But at the exam, you will have what I call the exam booklet, which is a set of slides that give you some technical information, and that is already available on Moodle, so you can have a look at it, and you will know what you don't need to learn by heart. Everything that is not in the exam booklet has to be in your head for the exam. The grading is given here, so it's a complicated formula that I'll let you discover, but the main thing is that the theory, and so the theory is made of 40% of the tests and 60% of the final exam. And the lab grade, which is given here, is the average of all labs with a weight of 1/2 for the first lab, which is shorter than the other ones, where we add the research exercise bonus, which is, as mentioned by Roman, an optional question. We understand that some of you are already familiar with some of the software techniques that we use in the labs. Then they may want to do more. So you can take those optional questions, which are small research questions. If you're interested in the topic of a given lab, you can take it, and it can give you bonus. And we will give you feedback. And there's also a small bonus for the social influence bonus that was mentioned by Roman, the Slack channel feedback that you give. The theory and where is my formula? The final grade is the mean of the theory and the practice, the lab and the theory, because this is really what TCP is about. There is some theory and a lot of labs, so ideally the lab should count more, but it's harder to have a true grading system for labs, so the average is the same. And the twist here is we take the harmonic mean of the two. Does anybody know what the harmonic mean is? Yes? It is? It penalizes lower grades, exactly. So we take 1 over the grade between 1 and 6. We take the sum, the mean of the inverse, and we inverse again, right? Which is like a contorted way of saying if you fail miserably at the theoretical grade, if you have 1 out of 6 as the theoretical grade, it's impossible to succeed. So you cannot make up by the labs, and vice versa. So, and if you are about the same at the 2, it's like the standard mean. This is the roadmap. We will start today with an overview of TCP/IP. So the course will be in 2 rounds. In a first round, today, we will cover everything. And then the second round will take the rest of the course. We need that because to do practical labs, we need already to be able to do things with the machine. So we need to have a complete idea of at least a bit of everything, which we will do very quickly today. And then you have the other modules as they are explained here. There is 1 lab per module, except the last one, because the theory always comes before the lab. The last week, there will also be no lab session. Questions on this organization stuff? If there is no question, then we move on to the technical parts. And as promised, we will go very quickly today through an entire view of what I call the TCP/IP architecture. The first remarkable thing about TCP/IP is that it is layered. So the word layer is used. A layer is something that we find in other systems. In software in general, we call that a module. To write good software, you have to make it modular. The idea of TCP/IP here is the same. We have to break the functions into blocks that fit together such that every function is smaller. Why we call it layer is that when you do communication, there is something special that you don't do one module that is alone. This module is always communicating with another one. So layers mean simply modules that communicate with each other, that are peers. Depending on the textbook you will read, you will find 7 layers or 9 or 5. it's largely irrelevant and everybody can argue what they are, but it's usually well understood that there are those 5 that I'm showing here. The application layer itself tends to become the bigger one and is split into subpart. But roughly speaking, we can divide them into those 3 groups. The physical layer is about transforming bits into physical things, like most of the time radio waves that are in the visible light for optical fiber, or radio waves on non-visible radio waves in general. That's not the topic of this course. This is the focus on the digital communication course. Then we have 2 layers in green here called the network and the MAC layer. They have to do with connecting systems together, connecting at a low level, making sure information can go from one machine to the next. Then the blue layers are the software layers. The blue layers are about connecting applications together. Why there are transport and application, we'll see that in a second. So what we will do today is we will go very briefly through the 4 layers, and we'll say a few things about the physical layer too, that will allow us to get started. The application layer is the most visible and interesting part of the internet. We'll say a few words about it, in particular about things like quick and application layer frameworks, but perhaps in its simplistic, most simple form, when you access the web, ignoring security, we'll come back to security a bit later, what you do is you have a web browser that communicates with a web server. So for each of those 2 machines, they have the illusion that there are only 2 machines. When you click on something, the web client sends a request to a web server. At this level, there is what is called a protocol. The protocol is the rules that govern the interaction of 2 entities, 2 or more entities that are at the same level. So a web client and a web server use a web protocol. The web protocol is called HTTP. Of course, application layer is the most interesting thing, but it's not the topic of this course, as I said. The transport layer, which is less visible, but is one that we will cover in detail, is serving the application layer in a generic way. Whenever you write an application over a network, you have to do things like transform a block of data into the things that a network understands. A network understands things like IP packets that we will discuss in detail. So this transformation has to be done by an application. Instead of having every application do it, we do it once for all, and we call this the application layer. The first thing to remember in TCP-IP is that there are, in fact, 2 transport layers, TCP and UDP. TCP-IP is a misnomer. TCP-IP means the entire set of protocols of the internet. And the most spectacular ones are 2 protocols called TCP and IP. So here is TCP, that is coming. TCP is what we call reliable. Reliable means if I send one piece of information from A to B, it may be, unfortunately, that some elements of that information are lost. As we will see, that's one of the key central and recurrent problems in the internet. You can never guarantee that a packet is received without error. In order to guarantee this, you need to do some work. This work is done by TCP. TCP will do things like put numbers in packets and count and ask the destination to send an acknowledgement that which number have correctly arrived, and if it sees that some numbers are missing, it will retransmit it. So this is what TCP does. TCP does it for you as an application developer, so that if you use TCP, you don't have to worry about missing packets. You just have to use TCP, send your data. If anything goes wrong, it will be handled by TCP. Right. TCP has one peculiarity. It is what we call a stream service. So, second thing to remember about TCP, it's reliable, but, there is a big but, it is not behaving the way we would expect it. The way we would expect it is, I have a chunk of data to send, an image, for example, a JPEG file. I would like to use a TCP interface, put the image into this interface, forget about it, and have it sent to the other end. Which is more or less what happens, with a small difference. What TCP delivers is bytes of information. So your JPEG file will arrive at the other end as a stream of bytes. So the application program that reads this JPEG file will need to pull the bytes one by one recognize when it's the end of the JPEG file, because perhaps it's not just one image but two. So the second one will not, TCP will not tell you that's the end of the message. Here comes another message. No, TCP will give you a stream of bytes. Second thing to remember about TCP. This means, of course, that the application layer needs to put some format into the messages that it is sending. If I send you an image, there will be what is called a MIME header that says when the image starts and how it is encoded. And when I read the bytes given by TCP, I have to analyze those headers. And if the header tells me the next 10,000 bytes are the image, then I count 10,000. And when this is gone, I know that the image is over. So this is TCP. UDP is another version of the transport layer that is different. So an application has to use TCP or UDP, but both ends have to agree. They both use TCP or they both use UDP. If you use UDP, you don't get reliability. So UDP is a very shallow transport layer. In fact, it does practically nothing. We'll see in detail it does a few things. But at this first round of approximation, it does nothing except it guarantees you that a message is delivered as a message. So it doesn't have the streaming problem of TCP. If I send an image using UDP, I send it in one or several packets. Then when I receive, the application program asks UDP, give me what you have received, it will send the image. Or nothing if a packet has been lost. So UDP will not deliver anything if it's lost, but if it delivers something, it delivers what was sent as one message. So we say it's datagram. We say it's a datagram service. Datagram means this, it sends one message as a message, whereas TCP sends a streaming service. But UDP is not reliable. Why do we have both? Why don't we always use TCP? Well, we'll come back to that. One of the reasons is TCP has a cost associated with it. In order to be reliable, it needs to do what is called a handshake. So before sending 1 byte of information with TCP, you need to do a few things before to put in place some synchronization data, some data that exists at both ends. So if you have to send very short things that fit in one message only, you typically don't use TCP. We'll come back to that. We continue going down through the layers. The next layer below is the network layer. So the network layer is solving the problem that's illustrated here. You want to interconnect the millions or hundreds of millions or billions of devices in the world. How do you connect them? Well, you can pull radio links or cable between all of them, but of course this is not efficient. It's impossible. So how does it do it? It uses what is called intermediate systems, like the post office does. So the model of the internet is that of the post office. You put your letter into a mailbox. A postman comes and puts the mailbox to the next post office switching center that analyzes the destination address, sends it to other switching centers. That's exactly how the internet works. Though at the beginning, the internet, what was the very first versions of the internet, did not use this system. They used what is called store and forward. With store and forward, at the beginning of the internet, the routers were computers, and the computers were expensive, rare things. On a campus like EPFL, there were 2 or 3 computers at all for the entire computer. So one of the computers was used as a switching center. So if I would send a message from A to B, the message is sent to the next computer that sends it to a next switching center and to the final destination. So the entire message is sent from place to place. At that time, entire messages were not very large, but we can wonder what would happen if we do that today. Well, today, what we do is to use packet switching that was invented by a French guy in 1974. And the key idea, that's the one that is still dominant everywhere today, is to break any piece of information into standard containers that have a maximum size. Now, the maximum size depends on the technology, but by default in the internet, it's around 1,000 bytes. Up 12,000 bytes is 1,200 bytes is the most common size. And those are called packets or datagram. If we use this analogy, if I send a mail over such a network, the mail is broken into chunks, into packets that reach the next intermediate system, which is now the mail server. And now the mail server recreates the entire message from all the different packets and send it perhaps to another intermediate mail server that sends it perhaps to the final destination. That's a typical case of what happens when we use email. We have our own mail server, the destination mail server, and between those mail servers we use IP, the network layer, and between the client and the mail server we use IPs. Did you observe anything specific about those messages? How they were sent? Yes? Some did, some took different paths, exactly. That may happen, although we try not to have that too often, but every packet in the internet is like a postcard, is an independent entity. So one of the functions of the transport layer is to hide this fact from the application layer. So a TCP will transform things that come into packets that may come in different paths. If they come in different paths, they may come possibly in different order. It's possible that packet 3 arrives before packet 2. TCP will hide all that stuff away from the application layer programmer and give the illusion that I have a fixed pipe that is sending bytes. Why do we think that we moved historically in 1974 from store and forward to packet switching? What is the benefit? Speak up. Okay, I'll do it again. Who has speak up working? Good, good. I see only one answer, so I was wondering. Can you guys try it too? And your role in the room number that's written here? 21, 490. Okay, now it's better. Okay, I close the poll. And you can see the results on your device. So majority thinks that it reduced the buffers required in the routers, which is the correct answer. So the possible things we may think of is that it reduces the delay and the storage required in routers. This is explained on this graph here. Here I'm showing what we call a time-space diagram, something that's very useful to reason about timings in computer networks. On the vertical axis is time, on the horizontal axis is space. So I'm showing a packet going from one place to the other. One remarkable thing here is that the lines are not horizontal, which simply means that the speed of light or the speed of propagation of signals is not infinite. Although everything is very fast, the computers are also very fast. They do computations in nanoseconds, and it takes nanoseconds to get through a few meters. So the propagation time does play a role here. If I send an entire message into a system that needs to forward it, like I do if I go through a mail server, the mail server has to keep the entire message until it forwards it again, which has two side effects. One, delay. Before being able to send it further, we need to receive the entire message. If the message is a video of 1 gigabyte, it will take some time. And another side effect is the storage required of the intermediate system. The intermediate system needs to store huge amounts of things. So in order to avoid that, we do packet switching. That's the motivation. Packet switching does not increase the capacity. We will see, in fact, that it might even slightly reduce it when we'll talk about the transport layer. The main motivation is this one, to have what we call cut through. This is what the internet is doing today. Here is a vision, snapshot of a few years ago of the EPFL network, the IP network of EPFL. The cheese boxes like this one are the classical drawings for routers. And you see lines, the green and the red lines that are showing interconnections between routers. Those are typically switches. We'll talk about switches a bit later. But for the vision of IP, we can think of them as lines connecting routers. And you see numbers. Those numbers are addresses. In order to use this system of packet switching, we need to have addresses. It's like the postcard system. When I send a postcard to somebody, I need to give the street address and the postal code. So the equivalent of that is called an IP address. The IP addresses, you see them marked as 128, 178, 71, 22. Those are, in fact, strings of bits. An IP address, shown here, is 32 bits. And as explained here, it's written by groups of 8 bits. So a group of 8 bits, like 128, is the decimal representation of a number that is occupying 8 bits. If today you have to write bits in a human-readable format, what do you typically do? You use hexadecimal numbers, right? One hexadecimal number represents 4 bits. When this was done in 1974, people were not so familiar with hexadecimal numbers, or they thought system managers would not like them, so they used decimal notation instead, which is a bit awkward because the number of digits is not the same. So any number here is a string of 8 bits, and the max number that you can see here corresponds to this bit, the string of 8 of all ones, which correspond to 255. So it's a group of 4 numbers that must be between 0 and 255. The addresses I've shown are the old address types. They are called IPv4. The current numbering system is IPv6. So there has been in total 6 versions of the Internet protocol. Versions 1, 2, 3 were experimental and were very quickly deprecated. Version 4 was the first one that went public. Version 5 is an accident. It is not at all IP. It's the protocol called ST2. And the next version is IPv6, which is probably the final one. Probably for the centuries to go, we will stay with IPv6. Why will we? Simply because the size of the address space is what matters. If you have 32 bits, that means you can address how many devices? Yes? 2 to the 32, and that's how many? 4 billions. 4 billions. So 4 billions was huge when this was done. Remember, there were a few computers per university, so 4 billion was an astronomical number. But now that everybody has several devices, and we are several billions on Earth, perhaps 10 billion soon, so that is not sufficient. So the IPv4 address space is not sufficient, so it has been increased to 128. So we multiply by 4 the address space, which means we put this to the power 4. And then this number is truly astronomical. We will never, never exhaust this quantity. Yes?
But people won't expect that you do back in the early days of IPv4. So maybe in 20 or 50 years, somebody would give that course and saying, okay, we're sure IPv6 would last forever. How do we know that this exponential trend is going to continue?
Well, it has to do with the population of Earth, right? We will not grow into billions into 10 to the power 1. So the number of bits of an IPv6 address is 128, right? So it's 10 to the power 36 or 37. So even if you give zillions of IP devices to everyone on Earth, you can still give an address to each of them. Of course, I don't have a theorem and a proof that says this will stay forever. Perhaps I'm wrong, but it's very, very likely that it will take a huge time, an astronomical time, to exhaust this. IPv6 addresses are written using hexadecimal numbers. So here are examples. An EPFL IPv6 address is 2001. I say 2001, it's formally incorrect. It's not the number 2001, it is 2001, but it's an hexadecimal number. But it's 2001 because it was standardized in year 2001. 620.618 is a prefix, that is the prefix allocated to EPFL. Right? So if you see anywhere in the world 2001-620-618, in fact, it's EPFL. And 1A6 is a prefix allocated to a part of EPFL, as I will explain in a minute. Right now, what we need to know about IPv6 and IPv4 is that they are incompatible. If you have a device that speaks IPv4, if you send an IPv4 packet to a machine that runs only IPv6, it will not understand it. It will not work. So we're ready to restart. Yes. We have seen that IP requires numbers. Those are the zip codes that are put into the IP packets. IP uses also names. Names were originally invented to be human readable. That was before Google. Before Google, if you wanted to go to a site, you needed to know the name, www.epfl.ch. So names today can be pretty much anything. They are structured. They go from less specific to more specific. We'll talk more how it works in details towards the end of the course. For now, what we need to know is that those names are, in principle, synonyms for IP address. So to every name, there corresponds an IP address, but it's not an exact synonym. A name can correspond to several IP addresses, and some addresses can have no corresponding name. The final part of a name, if it's 2 digits, it's a country code, NZ New Zealand, CH Switzerland, GL, you can look up in Wikipedia, it must be one obscure country, a small island somewhere. All others are either the 3-letter ones are the historical domains. .com were originally for commercial. And then pretty much anything can be a name if you're willing to buy it. So for $500,000 or francs, you can buy your own name if you want, $500,000 per year. Right? The important thing is that names have to be mapped to addresses. So here's an example where Elaine goes to a website. The website is ssc.epfl.ch. So she clicks on a web page that contains a link to this. So there's an HTML text that somewhere contains this address. And if you click on it, you open the page that is behind the link. Right? What in fact happens before your computer can connect to this page is that your operating system has to do what is called name resolution. It has to find what is the IP address of this web server. The IP address is not in the web page, but is needed. So you will go to another server, which is called a DNS server. DNS stands for the Domain Name Systems. DNS servers are big databases that contain all the names and the corresponding IP addresses. So this computer here will first send a message to the DNS server that will then hopefully respond with the IP address of this machine here. So this machine, ssc.epfl.ch, happens to be today available at this blue address. It's only now that your computer is able to connect to this machine because inside the IP packet header, the part of the packet that's used to know where the packet has to go, there is no name. Inside the IP packet header is only the destination address. Then the web server, hopefully, will respond to Elaine with a page. By the way, how does the web server know what is the IP address of Elaine's computer? Yes?
In response to the source address that you received from the packet in which you received the request?
Exactly. So in order to know the IP address of a server, you need to go to the DNS server to know what is the IP address. But of course, we don't do that in the reverse direction. We always put in every packet the source IP address. So when a server receives a request, it knows whom to respond, doesn't have to go to DNS to do that. It simply responds to the source address that is contained in the IP packet. You do the same when you send a letter. If you want to get an error message from the post office in case the letter cannot reach the destination, you put also the source address. The same happens here. So that's for the IP layer. Now, there is a somewhat less obvious part of networking, which is called the MAC layer. Both the network layer and the MAC layer are used to interconnect systems. The MAC layer originally was made for what is called local area networks. It was made for interconnecting systems at a local scale. In fact, the very first computer networks until the beginning of the 90s were only enterprise networks. So they were made relatively small-scale networks here. So the MAC layer, we can think of it as a mechanism to interconnect a number of things that are in the same room or in the same small apartment here. It uses either cables, that's an Ethernet switch that you have seen, and if you haven't seen it, you will see some in the labs, in Lab 2, or more frequently what you use is the Wi-Fi local area network with the Wi-Fi base stations. One of the key things, of the MAC layer is that it interconnects systems without any configuration. Without any configuration means in the IP network layer, when I interconnect two systems, I need to give IP addresses. So if you've seen, when you're here at EPFL, your device has an IP address, which is an EPFL IP address. When you go home and you're served by Swisscom, you have a Swisscom IP address. So your IP address has to represent the network to which you're connected. So somewhere there must be some mechanic to change your address, to allocate it. The MAC layer, the job is different. With the MAC layer, we want that it works without allocating any addresses here. So those addresses, there are addresses in the MAC layer. They are called MAC addresses. And we can think of them as essentially hardware addresses. When you have a Wi-Fi adapter in your system, or an Ethernet adapter, it comes with a number that is called its MAC address. It has lots of numbers, but one of them is its MAC address. It's a hardware number that's carved into it by the manufacturer. It's 48 bits, and it is used as an address. So the mental model is the following one. When A sends a packet to R, in that case the router, it puts in a destination field the destination address of the router, which is a 48-bit string. Every device can potentially see it, if it's on Wi-Fi, for example, but only the devices that think it is their address should copy it, except if the devices are doing packet sniffing, in which case you can also copy packets that are not for you. This is how the MAC layer works. So the MAC layer address is a hardware address. It has no meaning of where you are. When you are with your iPhone or smartphone at EPFL or at home, you have the same MAC address, but you're in different networks. Question?
How long until you run out of MAC address?
How long will we run out of MAC addresses? They're 48 bits, so it's 16 bits more than the 32 bits of IP. So there will be collision sometimes. So there's a provision to extend it to 64 bits. But as we will see, this is less severe because MAC addresses have only local scope. To have a collision, you need to have the same address and to be, by accident, in the same local area network, roughly speaking, in the same room. We'll talk about that a bit later. Right now, what we can think of is that a local area network is a system that allows to interconnect several devices through a Wi-Fi base station or an Ethernet system. Right. Now, if we want to interconnect more than a few systems, we typically go through a router. So a typical interconnection is this one. You put a router between several LANs. So at the origin, the idea of IP was to interconnect local area network. That's why it's called IP. I is interconnection, internet. It's not a network. We're not speaking of the net, but of the internet, because the origin of this was to interconnect networks, and the networks were the local area networks. For this to work, any machine must know what is the IP address of its router. The router is called the gateway in old terminology of the 70s that has survived up to today. Right. So we need to dive into a few details that will help you do the first lab. Machines need to know their IP addresses. You also need to know the IP address of other machines going to the DNS, but that's not sufficient. You also need to know something specific, which is your network prefix. What is the network prefix? Well, if you look at this snapshot of the EPFL network, you see that all EPFL addresses have something in common. What do they have in common? The prefix, which one? Not the first three. In fact, the first two blocks of number, 128, 178, means EPFL. In fact, 128, 178, and 128, 179. So it's the first 15 bits. That means EPFL. But let's ignore this 15 versus 16-bit subtlety and think only of the first 16 bits as meaning EPFL. That means EPFL, but EPFL is not one big local area network. It's made of multiple local area networks. And one of the principles of IP is that two systems that are on the same local area networks should have something in common, which is the beginning of their IP addresses, which is called the prefix. At EPFL, the prefix is the first 24 bits, the first 3 words of the IP address. So if you connect two systems on the same Ethernet switch or on the same Wi-Fi base station, they must have the same 24 bits in their IP address, which means if you move somewhere else, you need to change your IP address. Also, even if you move inside EPFL. We'll see there are a few tricks to handle that, but that's the basic principle. So those addresses that are shown here, they have in common 128, 178, 71 also. That means they are on one subnetwork of EPFL, which is the 71 subnetwork. If you look, there are other subnetworks. There is the 15 subnetworks. That's the network of EPFL where all the DNS servers and things like this are located. So it's one of the critical subnetworks of EPFL. And then every lab or every floor of EPFL has its own third word of the address that represents a subnetwork. Now, in the best of all worlds, it would always be like at EPFL. The prefix is the first 24 bits. But this is not how things are. For example, at ETH, our sister school, the prefix is 26 bits, not 24. So 26 is a bit clumsy, but that is why, because it doesn't correspond exactly to the grouping of bits into decimal numbers. So the conclusion of that is that there's no rule about what is the prefix. Sometimes very often it's 24 bits, but not always. So the systems, the hosts, need to know how many bits is part of their prefix. So we need to give that information. The information, for example, 24. We need to give that information so that host knows I am in this subnetwork. Why do we need that? We will see that in a minute later. It's important, for example, that this machine here knows that it is in the same LAN as this one. Why do you need to know whether you're in the same LAN as another one? Because of one rule of IP that says if A sends a packet to B, the first thing that A needs to know is B on the same local area network as me? If yes, I send it directly to B. If not, I need to send it to a router. So I need to have another configuration somewhere that gives me the IP address of a router, and I need to send it to the router. So I need to know, to do this test, is the destination the same prefix as me? And to do this test, I look at how many bits are in my prefix, and how many, do these here 24? Then I analyze the other address. Are the first 24 bits of this other address the same as mine? If yes, then I am in the same subnetwork. For historical reasons, this is often called a mask. So instead of saying it's 24, we find things like we say it is this, 255, 255, 255.0. So that's a computer science way of saying 24. Because what do? Here we put ones in all the positions that are in the prefix, so the first 24 bits, and 0 otherwise. And if I translate that into decimal numbers, all ones gives the number 255. So the translation of this binary sequence into a dotted decimal is this one. So it's a bit clumsy, but that comes from a historical reason where a simple way in assembler to decide whether the destination is the same prefix as you do the bitwise AND of all the bits of the mask and the bits of your address, and that will give you your prefix. That's the reason. It's completely obsolete today. There's no reason to do that, but most documentation will use this, so we are forced to use them. So for IPv4, it's doable. For IPv6, there's the same problem. IPv6 hosts also need to know what is the length of their prefix, and it can be given either with FFF things or with simply the length of the prefix. So we'll be exposed to that in the lab. Now we climb down the layers and we reach the physical layer. As I said, the physical layer is the topic of other courses. We won't do it here, except for side effects that it has on us. About terminology first. A physical layer is visible to us through its performance. And its performance is, one aspect of it, is the bit rate. Bit rate is how many bits per second a certain link can carry. Ethernet today is 1 gigabit per second most of the time, sometimes 100 megabit per second, sometimes 10 gigabit per second. In computer science, people call that bandwidth. I think they misunderstood some communication theory courses. The bandwidth is something about Fourier transform. It is in the spectral domain how wide a certain signal is. Of course, the bandwidth is proportional to, for a given channel model, the bandwidth is proportional to the bit rate. So if you want higher bit rate, you need higher bandwidth. But if you have less noise for a fixed bandwidth, you can have higher bit rate by coding things in a more intelligent way, by sending, instead of sending binary symbols, you can send symbols that are more complicated. So invariably in computer science documents, bandwidth means bit rate. But don't say that to Emre Telatar or others when you take a communication theory course. Here is the mapping between bandwidth and an example of mapping between bandwidth and bit rate. The topic of information theory is to say for a given channel of a given bandwidth and a given noise model, here is the available capacity, which is the maximum bit rate that this channel can achieve here. One aspect of the channel that is not completely transparent to us is the propagation time. The transmission time is, let me explain this diagram. So this diagram is showing a space-time diagram where this time time flows horizontally. And I'm showing here on the top what happens at the sender on, for example, a 10 megabit Ethernet link. This is how things are if you do an oscilloscope representation of the signal on the coaxial cable sent by an Ethernet system. You will see things like this. So it's a very simple modulation where if things go up and down first or the opposite, it means a 0 or a 1. The time it takes here horizontally to send 5 bits is the transmission time. It is how much time it takes to put the bits into the channel. At 10 megabits per second, it takes, in 1 second, you send 10 millions of bits. So it takes 0.1 microsecond to send 1 bit. That's the transmission time. The higher, the better. But, as we have seen before, when we transmit over the cable, there is some propagation time which is non-zero. This is the time here from T0 to S0. This propagation time is more or less fixed, is given by the laws of physics and by the speed of light. The only thing that you can influence is the material in which you transmit the signal. If you transmit the signal in open space, it is at 3 times 10 to the power 8. In cables, it's a bit less. So roughly speaking, you take 5 microseconds to do 1 kilometer. That's the propagation time. As technology evolves, that will never get better. As technology evolves, we go from Ethernet was at the origin 10 megabit per second. Now it's most of the time 1 or 10 gigabit per second. So we've multiplied by 1,000 the bit rate, which means we've divided by 1,000 the transmission times, but the propagation time is still the same. This has not changed, of course. And if you look at the time it takes to go around the globe, going around the globe is when you ping New Zealand. You send a packet to New Zealand and you wait for an acknowledgement. The propagation time of this is the time it takes to go to the other side of the globe and back, and that's 200 milliseconds, so 0.2 seconds. So it starts to be visible. It's visible also when you have telephone conversation to a very far place. You feel that when the other person is speaking, there's a delay before the signal comes to you. If you're doing gaming or you're doing a music rehearsal over the internet, that's one of the things, one of the problems that cannot be avoided. There's no way it will ever be avoided. So what high-frequency finance traders do in order to reduce that time, guess what they do? Yeah, they buy rooms near the stock exchange, so they have to be physically closer, which defeats the purpose of networking, but this is due to the speed of light. Here is, for example, 4 typical scenarios where I can compare the propagation time versus the transmission time to send one packet of 1 kilobyte. So here when I write 1K byte, the little k means 1,000, and the big B means byte, 8 bits, so 8,000 bits. In a data center, you have huge bit rates and a relatively small distance. However, even though the distance is small, perhaps 20 meters of cable, we see that the time to send a packet is the propagation time is larger than the transmission time. So because the transmission times are astronomically large, right? The opposite is true when you are in a local area network at 10 megabit per second and relatively short distances, then most of the time you spend sending a packet is due to transmission. And on the internet, depending on where you're going, you're probably also dominated by propagation time. And one of the challenges for protocols like TCP and IP and others is to work across all those conditions. You have to be able to have a protocol like TCP that works in all of these conditions. I mentioned bit rate, which is the capacity of a channel, or the achieved capacity of a channel. Very often we're interested in what we call throughput. Throughput is the useful bit rate that you get when you do a transaction. If you transfer a file from A to B, for example, you do a backup of your disk of 500 gigabytes, you transfer it from A to B, how much time will it take? The times is 1 over the time, so how many bytes per second you actually transfer, that's the throughput. That's the useful part of the bit rate. The throughput is usually much less than the bitrate, even if you interconnect when you're doing a backup from machine A to machine B, if you interconnect them with a cable at 10 gigabit per second, you will not get a throughput of 10 gigabit per second. You will get usually a bit less, or much less. You will get less, why? Well, one of the reasons is that, as we will see, there are all those layers. When I send 1 byte of information, I put a MAC address, I put also an IP address, so I put lots of information that is not useful information. It's used only for routing, for example. So this information is called protocol overhead, has to be transferred in the 10 gigabit per second. So it removes a few percent. But there are what we call waiting time. Here is an example of a simple protocol that you may use in the lab, and that is used, for example, when we send a query to a DNS server. I'm showing here a space-time diagram. Time flows horizontally. And I have A that sends a packet to B. So here I'm not showing all the bits of the packet, but just one packet here. So there is a time, which is the transmission and propagation time. Assume I'm using UDP, like we are doing when we send, when we don't use TCP, for example, if we send a single element of data. And assume I want still to be sure that the thing has been received. One way to do it is to request that the destination sends a response. Sometimes it comes naturally. For example, if I go to a DNS server and I ask the DNS server, what is the IP address that corresponds to that name, I expect the DNS server to respond. It will either respond, it's not me who knows, try someone else, or it will respond with the correct address. So you expect a response. If you don't expect a response, then you still force the system to send a response, which is called an acknowledgement. It's empty data, but there is still the information. I have received this information that you're sending to me. Now, assume packets can be lost, like they can in the real world where we live. Then one way to make sure that you detect the losses is to see whether acknowledgements are coming. And wait if an acknowledgement doesn't come. So a simple method that is used everywhere, is used, for example, in TCP, is used in DNS resolver, is to start a timer. When I send a packet, like here, packet 2, I start a timer of duration T1. And if this expires before I receive an acknowledgement, I declare that this packet is lost, and I transmit it again. Of course, if you do that, you have to make sure that the duration T1 is larger than the round-trip time, because if it's not larger, you will expire before and you will have unnecessary retransmissions. So you need to estimate the round-trip time. Those are the kind of things that TCP does. Now, if we do this, what is the throughput of such a protocol? Well, it depends on the values of the transmission time. In the very optimistic case where I don't lose any data, you can tell me, well, if you don't lose any data, where's the problem? Well, here is where the problem is. There is still a problem. The problem is the propagation and transmission time. Here, I'm showing on the A line what happens when I send a packet. Then I send the packet, it comes here. I wait for the acknowledgement comes back. There is a time here in the middle, which is the round-trip time, during which I'm waiting. If this round-trip time is ridiculously small, because the propagation time is very short, then this is not a problem. If it's very large, this will affect the performance of the system. So we can compute the throughput very easily for that case by saying if there is no loss in a time interval that goes from here to there, which lasts the sum of all the quantities that are indicated, I have sent one packet. So I am wasting, in fact, all the part here that is in black or in green, which gives this fraction here. So if the bit rate of the channel is B, the actual throughput I have is B divided by something. This something contains two elements, 1 plus 2 elements that are the penalty term. One is the ratio of the overhead of the acknowledgement. I had to receive an acknowledgement. That takes a bit of time. And the other one, 2dB, is what we call the bandwidth delay product. 2D is the round-trip time, B is the bit rate. So 2dB is the number of bits that are transmitted over a channel during the propagation round-trip time. So those are what we can call the bits that are on the fly, that are in the pipes. Those are the bits that I cannot stop. When I've sent them, if I want to stop, for example, they are flying on the pipe. So this is a number that captures whether a given channel has a lot of latency or not. If I analyze the performance of this simple retransmission method that is called stop and go over the 4 cases I mentioned before, we find that in the data center case, as well as in the internet case, the performance of this is ridiculously bad. If we would do this when we transfer files from A to B in the data center or over the internet, we would have a throughput that's a few % of the total link capacity, which means most of the time we're in fact waiting because most of the bits are always in the pipes rather than somewhere else. If you do this at low bit rate, which are given here, then you can do that. Then the performance is very good. So TCP is used in those 2 cases. So as we will see, TCP will need to do something smarter than simply send a packet, wait for an acknowledgement, and if it's declared lost, retransmit it. You'll need to be a bit smarter, not very much smarter, but a bit smarter, and we will see that later. If you are in cases like this, you can simply do stop and go. So you do stop and go, for example, when you have a low-speed interface in a controller that's controlling some electronic equipment, and you want to send a signal. If you're sending the signal at a few kilobits per second, then stop and go is good enough. But if you send it at terabit per second, you will need to work harder. So this is where performance will play a role in the design of the protocols. So we'll come back to that when we study TCP in detail. Now, what we will do for the rest of today is to put things together and see how things are, and this is an introduction to what you will have to do for Lab 0. Here I'm showing a scenario where I have 2 local area networks, one that is cable over Ethernet, so devices that are connected to an Ethernet switch on the right, and devices that are connected to Wi-Fi, and they are, between the two, I've put a router, which is a very classical configuration. And we will observe what happens when the web server sends a file to the device on the left, which is Elaine's device here. I'm showing the 5 layers that we've seen and what happens now when the file is sent. So what the web server does first, The application, which is the web server code, will issue some interface to the transport layer, interface request to the transport layer. In that case, it's called the socket layer. And one of the functions that the socket interface offers is, for example, send. So in the code, in the Python or C++ code of the application server, you will see a line that says send S2 and some data. S2 is the name of the socket on which you send the data. We'll see in detail the sockets. In Lab 3, we'll do some socket programming. But right now, this is what will happen. So this is a pure interface inside the machine between the operating system and the user space, typically. Then the transport layer, which typically in Linux systems at least is part of the operating system, will do its work, and its work consists in hiding the fact that the network is packet-based. So it will, in that case, create 5 packets, 5 blocks, out of the perhaps video file or the image, and will pass them to the network layer. Passing them to the network layer means we add to those packets an IP header. That is, for example, containing the destination address, the IP address of Elaine's device. That is in the green part that is shown here. Then this will be sent over Ethernet to the router. Sending it over Ethernet requires adding the Ethernet destination address of the router, which somehow this device will need to know. We'll see how a device knows what is the MAC address of the router that it needs to speak to. There is a special trick for that. But right now, the only thing we need to know is that this red address is put in front of the green address and other details that is now called a MAC packet. Now the MAC layer on the cables through the switches will do the job of transporting this packet to the router. So this packet will be transformed into physical layers. And this, here I'm showing the first 3 packets, are received by the hardware. Typically, MAC layer is done in hardware. IP and transport layer are done in software, but this is typical. There are systems on a chip that do everything in hardware, and there are also some software implementations of the MAC layer. But typically, the hardware will receive this packet, the hardware at the router, will read the destination MAC address, we'll see, oh, that's for me. We'll remove the destination MAC address and pass it to the operating system that will then analyze the IP address. And if everything is right, the IP address should be an IP address that's on the path to the destination. Here it's a router. So the router will read the IP destination address, and the router is an intermediate system. It's not the final destination. It is something that's in the middle. We call it an intermediate system. So the router will analyze this IP address. It has a routing table, very much like the post office when you send a packet to Zurich and it analyzes the digits and it's 8,000 something, or we have to put it in a train to go in this direction. So the router will look up at the table and will decide, oh, I need to send it somewhere else. Somewhere else is where? Well, it is on the Wi-Fi interface of the router. So the router will send the packets again to the hardware, to another piece of the hardware. And the packets will have now a different MAC layer header that contains the information that's necessary for Wi-Fi, that contains, among others, the destination MAC address, which hopefully is that of Elaine. It will be transmitted to Elaine's machine that will do the reverse. All the layers will strip off the things, and we will receive, hopefully, in the normal case, the 5 blocks, but of course, anything in between can happen. One of the packets may have been lost, in which case there will be retransmissions and lots of things that we will see in detail. But here, assuming nothing gets lost, the transport layer will then make it available. If the application is doing nothing, it will be received and nothing will happen. Hopefully, if your web client is getting things from a server, the code will issue a read. So the operating system will buffer the data, keep the data in a buffer, until the code does a read, and when it does a read, it will display it to the application. Those are how all those layers are interleaved. Question?
Does the router have an IP address?
Sure, yes.
Then I do not understand why do we need MAC address. So imagine that the web server wants to transfer some data to router through Ethernet. And in MAC layer, a MAC address of router is added to every IP packet. why do we need to add MAC address? Why can't we add another IP address of router?
So the question is, why do we have MAC addresses and IP address? That's a very good question. And probably, if we would design all that stuff today, we would not have MAC addresses. Probably. I'm not 100% sure, but probably. So your question is completely valid, and it looks artificially complicated. And it is. It is this way because of the evolution. This is how things have evolved. At the beginning, the first networks did not have IP. Right? The first networks were local area networks only. So they used only the MAC addresses. So when I was a student, I was working on networks like this. We did not have IP address. We had BitNet, Multics, things like this. Novel, NetWare. Those are things that are still visible today. You could interconnect a few Windows PCs together. They did not have IP addresses. They used only MAC addresses to communicate. Of course, it did not work very well, and someday somebody invented the web and wanted to go a bit further out than just in local area network, and we added the IP addresses. But they came second. This is why we still find them today. Now you can say coming second doesn't mean you cannot supersede everything. We could have a new version that deletes the MAC addresses. There is one, as I mentioned, there's a fundamental difference between a MAC address and an IP address, which is subtle, but it's practically very relevant. The MAC address is the address of a hardware. Assume you come tomorrow in a room, you have two devices, and you connect them together. With MAC addresses, there is nothing to do. They will talk to each other without any kind of configuration. With IP, you will need to do some kind of configuration. You will need to allocate the correct addresses. So the IP addresses are manually assigned addresses. Of course, we don't go manually and assign them. There are automatic ways to replace that, but we need servers that allocate the addresses. They are called DHCP. You probably have seen that already. You need to allocate the IP addresses. The MAC address, you don't allocate them. They are burnt into the hardware, and that works. So that's a very convenient way to bootstrap communication. For example, we will see that when you connect a device like this one to a router, in order to configure the IP address that this one needs, we will use the MAC address to communicate. So in order to make things automatically, in order to bootstrap, I am on this local area network, I need to have this prefix. But how do I know that I am on this local area network? I need to talk to some server of some kind. But in order to talk to some server, I need an IP address. So I have a bootstrap problem. This bootstrap problem is solved by using the MAC layer addresses. It could be solved by other means, but this is how it is today. That's why we have both. A bit of terminology. I've mentioned the word packet. A packet is any of those blocks. Very often we use different wording. So a packet at the TCP layer is called a segment. At the IP layer, it's called a packet. And at the MAC layer, it's called a frame. It's not a strict terminology, but very often you will see this. Yes, that's. Here's another view, which is equally important. That's the one you will see in the lab when you use some of the tools we ask you to use for Lab 0. Here I'm looking inside the packet. So when the web server sends a packet, as we said before, it puts it into a MAC layer packet, which is called a MAC frame. The MAC layer packet contains a header that has the most important information is the MAC address, but it will contain other things. The source MAC address also, for example. And then what we can think of as the MAC payload, which in fact is an IP packet. And inside the IP packet, there is the same thing. So that's why we call it an onion. There is an IP header that contains the IP destination address, plus other things, and the IP payload. Now, if you're using TCP, TCP does things like it numbers the packets to know which packet is missing in order to retransmit it. So all those numbers are put in the TCP header, plus other things like port numbers we'll talk about later. And it's only in the TCP payload that you have application data that's useful for the application that's using the socket layer. Right? For example, the bytes of an HTML file. In reality today, you're probably likely to have also an encryption layer between the two. In the lab, you will see how those things, we'll use tools like T-Shark and others, Wireshark, to see exactly what's in the packets. That's one of the crucial tools when you want to analyze a network, understand how it works, debug potential problems. You look inside packets. That's one of the very first things we'll do this week. And inside packets, you will see things like this. So things like this, here, for example, I'm looking inside a packet, and I see an IP header. So all of this is not in the packet. So what I'm seeing here is a pretty print done by software, by the packet capture software, that makes it human readable. What is inside the packet is only bits. In particular, in the IP header, I will see the IP address, the destination address. So this one is truly inside the IP header. But I see here that my software has written things like lrcp33.epfl.ch, which is the name of the machine. Was this name in the packet? What do you think? No, it was not, because I said an hour ago it was not. So the name is not in the packet. So how could it be printed here? Well, this packet capture software has gone to the DNS to do what is called a reverse query. So before printing this, so the packet capture software has analyzed the packet, it has seen the destination address, then it had sent a query to a DNS server, which is called a reverse query, which is what is the name that corresponds to this IP address. It does not always work, but when it works, it gives you the name, and then it prints it. So don't be fooled. Those names are not in the packet. They are just done by the software that displays it. I will conclude with this last question. We do a packet capture by putting, as we've seen, a switch very often it's possible to sniff packets. If I sniff packet here at point 1, I put a packet sniffer here. I observe all the packets that are sent from the server to Elaine's smartphone. And with such packet capture, I read what are all the addresses. What will we see here in the packet at point 1? I propose several answers. Which one do you believe in? Close the poll in 5 seconds. And the majority is saying answer A, and as most often, the majority is right. At least that's what we believe. The packet is sent to Elaine. So the principle of the IP layer is end-to-end, so the destination address is the final address. But the packet is sent by the server to the router, so the MAC address must be that of the router here. It's simple, but that one is very important. Make sure you don't confuse those two addresses. The majority has answered right, which is a good sign. We'll come back to that and other questions a bit later. Voilà, and with 1 minute of advance, we will conclude for today. If you have any questions, use the Slack channel, the general Slack channel, which is for the lecture and for any organizational issue that's general for the course. If you have issues about the lab, use the Slack channel of the lab. Thank you very much. See you next week.